before he put on his pants. Now, I don't understand why that was going to get addressed faster. All right? But it relates to what we're talking about now, which is the idea of partial order. So we had the idea of a partial order. All right, so here's a graph, and in it, each node represents a task that you need to complete. And you can't do this task until you've done the task of all the arrows coming in. All right? So we call this a partial order because there's some order, there's some, you can put your socks or underwear in any order. You can put your socks and pants in any order, right? But you should put your underwear on before your pants. Right? You hear what I'm saying? So the integers, for example, are totally ordered, right? Given any two integers, you know which one's smaller than another, right? Sets have a partial order, right? Because if one set is properly contained in another, you can say that the one is a subset of the other, right? Or a superset. But if they overlap in funny ways, then they might not be comparable, right? So this is a partial order. And what are we going to do with it? Our goal is, here's just two orderings, right? And what we're looking for is, given the input will be a graph representing a partial order, and this, the input will actually be called what we call a DAG. What's a DAG? It's a directed acyclic graph, right? Why don't we have cycles? Because it'd be weird if A was strictly before B and B was before D. If there was a cycle, then you have a problem, right? So we're given as input a DAG, and the output we want is a linear ordering. That means you want to order all the nodes in a way that respects the partial order, right? Particularly for every edge. If there's an edge from socks to shoes, then socks has to come before shoes. Right? Everybody got that? So we don't have cycles, I guess. All right, so we're going to do this algorithm by example. All right, we're going to go through this example, and it'll be pretty, and then we'll kind of show that it works by example. All right, so here's the input, and we want to find. So one algorithm is to find a sink. What's a sink? A sink is a node that has no outputs, right? And what do we know about this sink? In terms of our ordering? It can be the last one. Does it have to be the last one? I mean, this guy could be last, right? But it can be last. So our algorithm is to find a sink and put it last and remove the sink and repeat, right? You hit her. All right. All right, so now how long does it take to find a sink, or how do you find a sink? Anybody have an algorithm for finding a sink? Yeah. In fact, you start anywhere and you keep walking, and when you can't walk anymore, then it's because you found a sink, right? But that could take you time in, right? You have to walk through here. So that could be, the whole algorithm n squared, and we want to do it in linear time. All right, so, but the idea of using depth first search is good in that if you start here, you push these on the stack, then instead of restarting over, you use the work that you've already done already. You keep that on the stack. All right, so that's what our algorithm is going to be. Is we're going to choose a random node, an arbitrary node. It doesn't matter which one, right? And here we're going to choose D, and we're going to do a depth first search. So from D, we push on E, we push on G, we push on F, and now what do we have? Is we have a sink, right? So what do we do with this sink? We pop it off, and we put it last, right? Does that make sense? So you pop off F, and you put it last. It didn't come off, but oh, there it goes. As you pop them off, you put them last. So now what do? we're at G, so now if we were doing depth first search, we would have recorded that which edges out of G we've looked at already, right? I don't have this in the picture. But the next we go down to L. So we push L on the stack, and then we pop L, and L goes on backwards in the queue, in our list, right? So then what happens next? G comes off and goes in the thing, and then E comes off, then D comes off, and we've run out of things. Right? Everybody kind of got that? Now what do we do, you think? You choose any other node, say I, you just find some node that you haven't looked at yet, and do it again. All right? So we push things on, and then we pop things off, and that was good. All right? Then we choose some other node. This time we happen to choose B. You push it on, you pop it off, and now you put on A, you push them on, you pop them off, and that's our ordering. Everybody kind of get the algorithm? All right, so now our goal is to prove that it works. All right? So it's kind of like the proof we did for radix sort. You know, remember then we looked at any two cards, any two things, and we made sure they were in the right order. Right? So this is what we're going to do now, is we're going to consider what we want is to prove that the output of this thing respects all edges. Right? So what we're going to do is going to consider an arbitrary edge of the graph. There it is, UV. And we're going to prove that no matter what happens, U is going to be in the ordering before V. Right? It's going to respect this edge. And since we're doing this for an arbitrary edge, then it's going to be true for all edges. All right? So let's look at, we're going to do proof by cases. First case is suppose that U happens to go on the stack before V. It's just one case. Another case is V goes on first. But we're considering the case where U goes on first. All right? So what's going to happen now is it possible that U comes off, right? It would be bad if U came off first, right? Because then it would be in the wrong order, right? Is it possible that U comes off first? No, because U's not coming off until you've handled this edge, right? At some point, I don't know, it could be right now, you know, we might go from U to V, or we might go somewhere else, right? But whatever happens, U's not coming off until V goes on. All right, so that's what we're kind of, you know, because of the edge, V goes on before U comes off. And so now we're pretty good, right? Because at some point, V will come off, and then at some point, U will come off, and we have them in the right order. Everybody good? So case 2 is that V goes on the stack before U goes on the stack. And it's certainly possible. Somehow we were going down here, and we came to here, and there was an edge coming the other direction. It's completely possible. All right, so let's break this into two. All right. All right, so I guess this is a subcase. We're looking at, this is case 2.1. You know, if V comes off before U goes on, then we're still good. Right? So the third case is that V goes on first, and then U goes on before V comes off. Right? This is the third case. Everybody see these are just the cases. Now what's wrong with this case? It's going to be a problem case, right? Because U's going to come off, and then V's going to come off in the wrong order. And you know what the problem is.
In order for that to happen, you have to understand.
Yeah, did you guys actually cover this?
Yeah. I was in that course.
Good, right. So this means there's a cycle, right? Because this is path from U to V, and there's this edge. Oh, there's a path backwards to U, and then there's an edge this way. And so we're good. Everybody kind of follow that? So that finds a cycle, and they're not supposed to be cycles. And that's the end of what we're doing. Any questions about that? So network flows is actually a topic that my father contributed a lot to. And I took a course from him in network flows. And let me tell you, 2 words of advice. Never take a course from your father. And never take a course from my father. Those are my 2 words of advice. All right? I worked very hard on it, and then got a good mark, but I did really, it was a disaster. All right, so anyway, network flows. We're going to do a quick little thing on network flows. We could, as I said, we could spend a whole lifetime studying network flows. First we're talking, before we get to network flows, we're going to talk about optimization problems in general. So the rest of the course is going to be about optimization problems. All right, so the input is going to, we specify a problem by saying what the possible inputs are, and for each input, there's going to be this exponentially large set of possible solutions, right? And for each solution, there's an easy to compute cost, right? So if I told you, here's an instance and here's a possible solution, you could really quickly tell me what the cost of that solution was. And the goal is, given a particular instance, to find a valid solution with optimal cost, right? So you're either trying to find a solution with minimal cost or a solution with maximum cost, depending on the game. Everybody kind of get what we're doing here? So for example, I remember this slide. Sometimes you have to really love PowerPoint. All right, so I don't know why it's doing this, but that's okay. So the input is going to be a network of pipes, right? It's going to have nodes and it's going to have edges between them. It's going to be specified by a directed graph. And each edge is, as I said, is a pipe that you can push water through. And each pipe has a capacity. So associated with each edge, UV, is the maximum capacity at which you can flow water. Welcome
nice.
here, welcome here.
Perfect.
All right, we just started network flows. And also, the graph will have a particular one node which is called the source, from which the water comes, and another node called the sink, at which water leaves, right? And the goal is to push as much water into the source as possible and have it drain at the same rate out the sink, and to do it at the fastest rate possible, subject to the constraints, right? So the goal is to find max flow. So here's an example of a graph. You can push 20 along here, and you can push 21 along here, right? So you want to try to find the maximum. A solution, as I said, tells you for every edge what is the rate of flow along that edge, right? And there's some rules. The first rule that is obvious is that the flow along an edge can't exceed its capacity. And we're also going to say that for every edge, the water is either, sometimes you can have a directed edge, but you can have an edge in both directions, right? And so you don't want water spinning around, so it's either going this way or it's going this way, right? So one of the directions is 0. Sometimes texts talk about negative flow, and I think that it makes the math easier but more confusing, so we won't do it. The other rule is we don't want any water appearing magically or disappearing magically. So what that means is that you look at any one node, so node V, this is the sum of the flow flowing into V, right? It's the sum over all U of what's flowing into V. And this is the sum over all guys flowing out of V, right? So the sum flowing into V equals the sum flowing out of V. Does that make sense? Of course, that's not true for after t because S, more is flowing out of S than coming into S because you can think about it as we're feeding it. We're feeding it some amount here and at the other end it's draining out. All right, so value of a solution is going to be, given a flow, a solution, the value of the solution will be the amount that's flowing out of S, right? But it's a little tricky because some might be coming back to S. So the official definition is the amount that's flowing out of S minus whatever comes back to S. I mean, it's basically what you need to feed into S to get it to balance, right? We're going to later prove that this is equal to the amount that flows out of T minus what flows back into T, right? Because since it's a closed system, what goes into S has to come out of T. And our goal is to maximize this flow. All right, so here's just a really simple example. Everybody can kind of look at this and figure out what the max flow is. All right, so here you got this. How much can flow along here, do you think?
1.
1. How much can flow along here? 2. How much can flow along here? 0. You could have stuff flowing back. Do you want to do that? No. So what's the max flow?
3.
It's 3, right? It's this plus this. So that's just what we're saying here, right? Already. You can't have more than 1 there. You can't have more than 2 here. These are going in the wrong direction. Another problem we're going to talk about later is the problem of min-cut. All right? So what a cut is I partition the nodes into 2 sets. One set contains the source, and one set contains the sink. And we look at the amount of the capacity going across here. Right? You'll see that there's a capacity of 1 across here, a capacity of 2 across here, and this is going in the wrong direction. Right? So at most 3 can flow across this cut. Right? People kind of see that? So, and it shouldn't be too hard for you to think intuitively that the max flow can never exceed a cut. Right? The flow across the cut. And in fact, we're going to prove that the max flow equals the min cut. Any questions? People kind of get the...
So we have to actually examine every node before we make specification.
Oh yeah. Yeah, we're going to do we're going to work very hard. Examining edges many times. Alright, so this is the same thing here as I've been saying. It's always true. That's just what I'm saying. Here's the flow equals the cut. Max flow is that, the min cut is 3, and these are always going to be equal. Alright, so there are many applications of network flows. One, of course, is you have factories that produce widgets, and you have highways, and then you have stores that sell widgets, and you have to flow them between them, right? But here's another application that you would never think of, which is to get people married. All right, so the input is going to be oh, sorry guys, but we're going to be against homosexuals here, I'm afraid. All right, we're only going to consider boys and girls matching up because the problem gets much harder when we look at matchings in general. All right, so we have boys here and girls here, and we put an edge between them if they're willing to get married. All right, and our goal is to match as many of them as possible. All right, and what is a matching? The Pope's involved here. So 1, Sam and Bob can't get married, and 2, Sam can't marry both Beth and Ann. All right? Don't ask me why, it's just the rules. All right? And similarly, Sue, you know, can't marry both Bob and Sam. All right, so we need these proper marriages, and we want as many of them as possible. All right, here we've managed to marry three couples. In this example, can you marry more? Anybody can kind of see? It's kind of hard to see.
Yeah.
Yeah, you can make it.
You can, yeah. Yeah, can you do better? Yeah, there we got 4 married. All right? So you might say, what does this have to do with network flows? Well, let me tell you. All right, so what we're going to do is we're going to take the graph of the blue, the blue edges, and we're going to make a network out of them. So these are the boys, right? And these are the girls, and these are the edges saying who marries who. And we're going to feed the boys from the source, and we're going to drain the girls. Sorry, from this to the sink, right? And now we're going to get max flow from source to sink, right? So, we need some capacities here too. On each of these edges, we'll have a capacity of 1, all right? And a little trick here is we're going to make sure that, well, we'll get to that in a minute. Capacity of 1, and what's that going to say is that the total flow, here the total flow into U can be at most 1, right? So the total flow out of U can be at most 1. And that's what says that a boy can marry at most 1 girl, right? And so over here, we put a capacity of 1, which says that the total flow out of V is 1. So hence the total flow into V can be at most 1. And so each girl can marry at most 1 boy. All right? People kind of following this? And so then, I guess that's the entire thing, right? So then you look for a max flow, and then if there's flow between the two, then you marry them. Right? Does that make sense? Now there's one little catch here that I didn't quite mention. Anybody see a bug in this algorithm? What happens if I had a flow here of 1, and then a flow here of a half, and a flow here of a half? Right? Then it's a legal flow. And in some ways it's a legal marriage, right? Because Bob here is marrying half of her and half of her, and so it's only marrying a total of 1 girl. Right? But, the Pope might not like it. So anyway, one thing we can also prove in our algorithm is that the algorithm we're going to use that if all the capacities are integers, then you're never going to introduce non-integers. So if the capacities are integers, then all the flows will be integers. And if the flows are integers and the flow is at most 1, then we know the flow is 0, 1, right? All right, so now let's think about a strategy how we might solve this problem. The first obvious thing is you're starting at S, and you see a capacity of 100, right? So you just push as much flow through as you can, right? And then you get a little fork, and you say, uh-oh, now I have to make a decision. Let me tell you a general rule of thumb. As soon as you have to make decisions, like think about doing those Sudoku puzzles, right? There's a decision, do I put the 3 here or 3 here? Well, you could have it wrong, right? And if you get it wrong, then you go forward, and disaster happens, and you have to back up and fix your mistakes. So as soon as you have to make a decision like that, it's a problematic, right? So maybe you decide to put the flow that way, yeah, but then you get stuck. So somehow you have to back up and put the flow the other direction, and it's hard. And we're going to be spending a lot of time talking about those kind of optimization problems and how to deal with it. All right, but here we're going to have a different strategy. The strategy is we don't try to get the we don't want to get as much flow going as possible because we don't know where it's going to go. Instead, we're going to take just 1 drop of water and get it from here to here. All right? So tell me an algorithm which will get one drop of water from S to T. Depth first search, breadth first search. Any of the algorithms that we talked about before, about all you need to do is find a path from S to T. You want to find is T connected to S. So you just search out from S and you look for T. Right? So that's what we're going to do. We're going to take one drop of water and we're going to shove it from S to T. We're going to have this path. It's going to be what we call an augmenting path. We're augmenting the flow that we currently have a zero flow, and we augment it with this drop of water. All right? So now we have a drop of water going along here, and well, that drop was really good and successful. So let's push as much along that path as we can. Right? How much can we push down that path? 20, right? So great, that was good, so we just push. We look along that path and we find the edge that has the smallest capacity, right? And we push as much through there until we reach our bottom. You know, that's our bottleneck. All right, so now what do? That was pretty good. So can we get more water through? All right? So this is what we're going to do, is I guess in this example, we first put the water down the bottom, and then we push water along the top. We can push 20 along the top and along the bottom. We can push 30, and that gives us a total flow of 20 plus 30 is 50. Right? And the way we're doing these numbers, I can have it sort of noted here. Every edge we're going to write two numbers. Right? The first number, the second number is the capacity, right, that you can't exceed. And the first number here is the current flow. All right? So this is the current flow that we have. We have 20 going along here, 20 going along here, 50 here, 30 here, 30 here, 50. And the reason that this is 50 is because it's taking the 20 and the 30, adding them together. Everybody kind of get this?
Why is it 30? Because didn't you say you're taking the smallest number from the whole thing? So on the first path you took 20.
Right.
So why are you taking 30 and not 10? Oh, because, okay.
Good question. It's probably had a spline here, which once this went up, this one wanted to go down. But the truth is, oh, actually, you can't even see this in this example, but this 10 is actually coming in the wrong direction. Right? So you had to take the 75.
Could you push another 1 from the 30 out of 31, and then push that up the 0 out of 2, and then push it down to 20, and then that
Have
way?
you taken this before?
No.
Yeah, it's good. Yeah, yeah. So
it just seems longer, though, by exact value.
yeah, but you know, water is amazing, you know? You get a little leak in your bathroom, and it will end up in your kitchen. I mean, I know.
So that's okay, like
Yeah, exactly. All right, so we're going to come back to that. We're going to think about it. We're going to do loop invariance, because we all love loop invariance. And what's our loop invariant is that we're given a legal flow. All right, so loop invariance that we have a legal flow, and right, so here's our legal flow. And what do we want to do is we want to push another drop of water through. All right, and so in order to do that, it's hard to think globally about things. In general, we're going to find thinking globally is hard, but thinking locally is easy. All right? So for each edge, local for each edge, we want to say how much more can go along that edge. And here, in fact, it's allowed 20, and we got 20, so you can't push any more through that edge, so we effectively remove the edge. Right? Well, this edge, there's 2 allowed, and we haven't done any, so you can still push 2 along this edge. While this edge here, you're allowed 30, you're allowed 31, but you only have 30 so far, so we can push 1 more through. Right? So we have a new edge graph here, and for every edge in which you can push some flow, we have it labeled with, hey, there's an edge here, and you can push that much flow. New flow through it, right? And so now, what you just talked about is even more apparent. Right? Everybody see that? So we're trying to push more flow from S to T, and so we find this new path. And so the next step is to do some sort of ST connectivity, meaning you do depth first search, breadth first search. You find a path in the augmenting graph from S to T, and here's our path in the augmenting graph, right? And then you look for every edge, what's the bottleneck, right? We can push one more through here, two through here, one more through here. I didn't write it down, you can push lots through here, right? So the bottleneck is 1 because of those two, so you shove one more through, and here we take this flow of 1, and we add the 1 along here, giving us our new flow. All right, so the 30 went up to 31, the 0 went up to 1, the 20 went up to 21, the 50 went up to 51. Right, everybody kind of buy that? So that's our algorithm here. In this example, can you get any more flow? Why not? Can you prove to me you can't get any more flow? Prove to me it, somebody.
You can't push any more water out of S.
You can't even get out of S, for example. And just as a little hint, that's a cut, and we're at capacity of that cut, right? You can't, the cut of, you can't even get out of S. All right, so now we're having this flow. We build our augmentation graph. Everybody see how we kind of build that augmentation graph? And then we look for a path in the augmentation graph, and there is no path. And the reason, I said there's no reason for path is because you can't even leave S. So we stop. Everybody got the algorithm? All right. So this is an example of what we call hill climbing algorithms. Hill climbing algorithm is the loop invariant says that we have a valid solution, right? We have a current flow, and you can think about that as someplace on a hill, and that the higher up the hill you are, the better your solution is. So my son is a great algorithmic guy. You know, he was little, and we were walking up a hill, and I said, you know, I was just starting teaching network flows, so I asked him, how do you find the top of the hill? And what did he say? Go up! Go up! That's his algorithm. His algorithm to find the top of the hill is simply go up. And I thought, brilliant, brilliant. Okay, now I asked him the next question. How do you know you're at the top of the hill? You can't go up anymore. That's our algorithm. Hill climbing algorithms. Yeah, yeah. So you keep, you know, you have a measure of progress, which is how good your solution is. You know, how do you keep going up? You keep going up, right? You make small local changes, right? You don't do big global weird changes. You make small local changes to your solution so that it gets better, right? And you keep making it better and better until you can't, local changes won't let you go up anymore. All right? Now, is this going to be the optimal solution? Not necessarily. Why not? I mean, think about standing on the top of a hill. Are you at the top, highest place? You know, not necessarily. Not necessarily. First off, problems, one is the running time. It could take you an exponential time to wind up the hill. That's one problem. Another problem is there could be a bigger hill. All right? So it means that there is a better solution, but local changes from here won't get you over there. You know, you have to make small local changes down. You're going to make big changes to get over there. All right? So that's the problem of local search hill climbing algorithms, is that you can find these local maximums, and they can take exponential time. So those are two pretty big problems with hill climbing algorithms, right? But people do hill climbing algorithms all the time. In fact, what is a classic? Anybody think of a real classic hill climbing algorithm that you probably haven't been involved in, but someday you might be involved in? I've been involved in it. I have 2 sons. It's called genetic algorithms. You know, you hopefully your sons will be better than you, and then you do hill climbing, and that's how we evolve, right? It's basically hill climbing. All right. All right. So here's our question. We just gave you an algorithm, right, for network flows. You make small local changes, and what are the local changes? Are I have a flow, and I make an augmenting path, and I augment that path, right? And then I have a new flow, I find an augmenting path, right? I keep doing that. Is it always going to find a global maximum, or might I get stuck in a local minimum? Right? That's something we have to look at and prove. Any feeling about whether we're going to get stuck or not? You can get stuck? He goes for stuck. Why do you figure we can get stuck?
Because if you do neural network programming, you have to change your algorithms sometimes to get out of.
You get stuck. Yeah, certainly. In general, it can be a problem. And the one way they do it is they put in random noise. They put in heat, which bounces you around. And if you have enough heat, it'll bounce you over these valleys and stuff. It can be very complicated. But on the other hand, oh, I guess it's just my belt falling down. I thought my pants were falling down. But don't worry, it's only my belt. All right, so. But here, we're not doing a real hard problem. It's only network flows here. So maybe for network flows, it will actually find a local maximum. All right, can we get stuck? And the answer is yes. And how do you prove that you can get stuck? I give you one example in which you get stuck, and that proves you can get stuck. Right? So here's an example. So here is the previous input, right? And here was the previous output, and we convince ourselves that that was a maximum. Right, so here's another input. What do you think about this input versus that input? It's the same. Right, but I just move the nodes around. And move the nodes around because the path that you liked, this one here, I just made it look more friendly. All right, so let's do the algorithm. And we won't do too many steps, but what happens is you push flow through here, and then you push flow here, and you push flow here, and you get stuck, and you don't have as much flow as you did before. People gonna buy that? And in the end, the amount of flow that you have is we push 2 this way, and then we only can push 19 this way because this is a bigger bottleneck. And then you only can push, so we get 19 plus 31 is 50, while before we had 51. Right, people see that? And the question that's going to arise is, okay, well, where did we go wrong, and can we fix it? Anybody get a sense of what? There's one edge here that we went wrong on. Something's wrong with that too, right? It's okay if you keep putting more and more in, right? Because what we're doing, this pushing algorithm keeps putting more and more in, but this edge got too much, right? And that's our problem, is we put too much flow through that edge. All right, so that's our problem. So in general, in hill climbing, right, I'm making choices, and I wander up here, it's bad. If I wander up here, it's good. And
for the other slide, does that mean you're supposed to try to push through the biggest one first?
Well, that's what we're going to. This is what this slide is talking about. How can we possibly fix it? All right. The one way of fixing it is at each point you make smarter decisions. Right? You think, hey, should I go this way or this way? Maybe I should have not put the flow in this path. I should have put a flow in another path. Right? So that's one thing, and I have no idea how to do that. All right? We don't have a sense of how to make better decisions. And so another option is when you go up here, you get stuck, you come back down again. What's the problem with that solution? Is you go up and down and up and down, and you don't know you're making progress. You can cycle, or you can just run exponentially long. It can be really a problem, right? So better switch of directions, hard. Try, back up and retry, exponential time. I was going to ask you another option is you get to take a bigger step. All right? If you had longer legs, then you'd be able to get up here. Right? So when we talk about taking a local search from this local search here, you can't go any further. But if you define your local search a little bigger, then you can avoid these steps. All right, so I don't know if this is going to help, but these are a bunch of solutions, right? And if you're currently standing right there, you know, you might say you can do a local search in one step to those, and you get some topology, right? Or you say, hey, I'll allow you to do a bigger step, and then you get a different topology, right? And maybe this different topology doesn't have local maximums, right? So that's what we're going to do. We made a mistake, and as was pointed out, you know, it feels that this edge was the mistake. Now, we don't want to back up, right? Because if you back up, then you might cycle forever, right? So we don't want our total flow to go down, but we want to decrease the flow on this edge, right? Because this edge is the mistake. We have to decrease this flow on this edge if we're going to find our optimum, right? Not that an optimum is unique. You could have different flows with the same optimum, but in this case, this is the only optimum, right? And to get there, we have to decrease this flow from 2 down to 1, right? So somehow we have to take a local step that decreases the flow on a particular edge while increasing the flow overall, right? Does that make sense? Any idea how to do that?
Maybe you could reduce one from that branches, make it flow downwards onto the 31 instead?
Yeah, exactly. In fact, what we're going to do, what we want to do is we want to add a flow here, right? Subtract a flow here, add a flow here, add a flow here. Right? Does that make sense? Right? We push flow forward along this edge. When I say subtract an edge here, it's the same as we want to push one here, push one here, push one here, push one here. Well, you're not allowed flow in this direction. But flow in this direction, we have a flow already in this of 2 here. So pushing a flow of 1 in this direction is the same as decreasing the flow here. Right? Does that make sense? So, how are we doing? 1 minute? 2 minutes, all right.
Question. If we already have 31 up to that point where the 2 by 2 starts up, why do we still have to push one from the top? Like, can't we just redirect one of them downwards and then we'll still have...
Oh, you're going to move it down here?
Yeah. Would that still not be, like, is that not enough to do?
Yeah, so basically what we're trying to do is we're trying to move this down here, and so it can come this way.
So why do we have to have the one up top?
Oh, because if you move it down this way, then you haven't increased your flow at all.
Oh, okay.
You're just redirecting the flow.
Okay.
Right, so that's the problem with that one. You're redirecting your flow, but you're not getting us any new flow. Right? And we want to make sure that, you know, our loop invariant rules are every iteration you have to make progress to make sure you don't cycle. So what we're going to do is we're going to, that's just what I said already. I said all that. All right, so, and this is also the same thing as if you're on a sidewalk, right? I can walk 75 this way, or I could walk 10 this way, right? And, right, you can flow 75 that way, you can have flow of 10 this way, like that. But if I'm at 15, how much can I walk this way? 75 minus 15, whatever that is. And the harder one, how much can I walk this way? Right, I can undo the 15 and then I can do another 10. Right, so those are the kind of games we're going to be playing here. You know, if you walk 5 that way, you get over to 20. I think we're going to run this. People, for some reason, have a hard time with these little things, so we'll do them next class. So, any questions about anything? Everybody happy? So, just let you know, we are a little bit behind, and so for the next test on Monday, next Monday, it's not like 2 days, 3 days Monday, it's 3 days plus a week Monday. The chances are we won't, unless we go really fast, yeah, we might have networks flows finished, but it won't be on the test. All right, because you need enough time to do it and think about it. So what's going to be on that test will be I told you already what's going to be on the test. There's going to be a graph theory algorithm which you have to come up using loop invariance. All right? And anything else? Everybody have your assignments, your tests here, and have a good weekend.